In this video, we're going to look more deeply into significant figures as a way of keeping track of uncertainties in a measurement. And we're also going to look at how we can apply scientific notation to make our life easier when we're using significant figures. Now, we've already mentioned significant figures before, and most of you will have taken chemistry before you have taken physics, so you'll have already been introduced to the idea of significant figures. So this is going to be a review of a lot of things you already know, hopefully, but I'll also be maybe showing you a few things you haven't seen before, so it's still worth going through this video presentation. Now, what are significant figures? As we've said, significant figures are used to estimate the uncertainty in a measurement. In other words, it tells us how precise a measurement is. And generally, when you're talking about significant figures, you're including all of the known digits plus one estimated digit. So let's look at an example here. I have a picture of a ruler, and there's an arrow here that is the length that we want to measure. So we could imagine that there's some block and it extends all the way here, and this arrow points to where the edge of the block lines up with the ruler, and we want to know how long the block is. So what's the measure of the block's length? And so we want to be able to look at where this arrow ends up, and we want to be able to read this. Now, the thing that we want to note is that each major line, that's the one with the numbers, 6, 7, 8, these are the major lines. These are 1 centimeter apart, and each minor tick, these are the little guys, they're 1/10 of a centimeter, a millimeter. And you can note that the 5, just to make it visually easier to see, there's a little, it's not all the way to the top, but the 5 gives a little bit longer, just so that you can visually see where the halfway point is. Now, if we look at our arrow, which tells us the length that we want to measure, we can see it is not yet to the 13. So it's not 13 anything, it's past the 12, it's past the 12.5, 12.6, 12.7, 12.8. It's not to the 12.9, so it's between the 12.8 and the 12.9. And so that tells us it's 12.8 something. The 12.8, those are the certain digits. It's definitely past the 12.8. It's not to the 12.9, so it's definitely 12.8 something. So these are what are the known or the certain digits. Now, the next digit over is the estimated digit. And looking at where the point of this arrow is, I estimate that at 5. So I'm going to make this measurement be 12.85 centimeters. And that is what I would measure. Now, if you were looking at this and you were to say, I think it's a little bit past the halfway point between those two lines, I'm going to call it 12.86 or 12.87. I couldn't really dispute that because this is my estimate of where the arrow lines up in between. So again, these 3 digits here, 1, 2, 3, 12.8, that represents the known or the certain digits. This 4th digit, the 5, that's my estimated digit. And all 4 of these together, the 3 knowns plus the 1 unknown, those are the significant digits in this measurement, or the significant figures of our measurement. Now, let's note, how many significant figures does this ruler have? We can make a measurement using this ruler to 4 significant figures, with centimeters being our unit of measurement. 4 significant figures. Now, let's look at another example. The arrow is now in a different place. And remember, each of these tick marks is 1/10 of a centimeter. And so if I'm looking at this, I see it's past the 12, it's past the 13, it's not yet to the 13.5. So I'm looking, I see 13.1, 13.2, 13.3, and it looks to my eye to be exactly on the 13.3. And so you might be tempted to write that as 13.3 centimeters, but that would be incorrect. Because how many significant figures does this instrument allow us to measure to? We just saw in the previous slide that we need 4 significant figures. So if it lines up right on that hash mark there, that tick mark, we would say that it would not be 13.3, but 13.30. If it were over a little bit, I might call it 13.31 or 13.32. that would be my uncertain digit, my estimated digit. But if it lines up right, if I'm estimating that it lines up right on that tick mark, I'm going to say 13.30. And that's a very common mistake that people make. They leave off that zero. And so I wanted to point that out so that you guys don't do that. Now, it's important to note that these rules about significant figures and about estimating uncertainties, they apply to any measurement. Every measurement that you ever make is going to have some uncertainty built into it. And so, how do you determine what that uncertainty is? Well, as a rule of thumb, if you're dealing with something like a digital instrument where you have, maybe you have a balance in your lab that's measuring how many grams something has a mass of, it will tell you, it'll be printed on the scale itself, or it'll be in the literature that comes with it. It'll tell you that the uncertainty of that measurement is plus or minus a tenth of a gram, or plus or minus a hundredth of a gram if you spend more money. It's going to tell you what that uncertainty is. Now, if you just pick up a meter stick, or you have an old-timey triple beam balance and you're reading between divisions like we did in the last slide, there's a really good rule of thumb for estimating the uncertainty. And for those kinds of, they call them not digital, but analog instruments, again, like a ruler, the good rule of thumb is that the uncertainty is about half the smallest division. In other words, let's take a centimeter ruler that's subdivided into millimeters. The millimeters would be the smallest division, so your uncertainty would be about plus or minus half a millimeter. Now let's look at another example. This is going to be an analog instrument. This is a picture of a graduated cylinder filled with a fluid, and we want to measure the volume of this fluid using this graduated cylinder. Now, one of the things that's tricky when you're measuring fluids in a graduated cylinder is that because of the surface tension in the liquid, you get this curved shape, and this curved shape is called the meniscus of the surface of the fluid. And you can see that I could measure up above or I could measure down below. And the rule of thumb is that for a concave meniscus, one that's shaped like this, you measure to the very bottom of the meniscus. If I had a convex meniscus, one where the shape was like that, you would measure to the very top of the meniscus. But in this case, we have a concave meniscus, not a convex one, but a concave one. And so we would measure to the bottom. And so I want to ask you, what do you think the volume would be? Let's say this is measuring volume in milliliters. So how many milliliters would you have here? Can you read that? I hope you recognize, based on what we just said, that this would actually not be 20. Now, if we look here, the bottom of this would be 20, but if it were up a little bit higher, it would be 20 point something between this mark and that mark, between this mark and that mark. So the 0.1 milliliter would be the smallest division, and so we can measure this to 3 significant figures, and so this should not be 20, but 20.0. And so again, we don't want to forget that 0 when we measure the volume of this fluid. So just make sure you don't forget that 0 when it's appropriate. Now, we've mentioned this before. Sometimes people use the word error when they mean uncertainty. The two terms are kind of interchangeable. But I prefer to use the word uncertainty because I find that the word error has an unfortunate connotation of being associated with a mistake. The fact that I say there's an uncertainty in a measurement just means that there's certain digits that I know what their values are, and there's a value that I'm estimating, so it's uncertain. There's a plus or minus. That's all we mean when we say that there is uncertainty in a measurement. Now, we can express our uncertainty in absolute terms. So we could say something like, I've got a measurement that's 4.35 meters plus or minus 0.05 meters. And this 0.05 meters, that would be the uncertainty of that measurement. I can also express uncertainty in relative terms. I could say that a measurement was 8.62 meters plus or minus 0.35%. That would be 0.35% of 8.62. And so that would tell you the uncertainty. This is called relative uncertainty. This is called absolute uncertainty. Now, we've said that one way of keeping track of our uncertainties is to use significant figures. And I know most of you, probably all of you, have seen all of these rules about how to use significant figures before. So I'm going to go through them pretty quickly. But if you get confused by any of this, just let me know, and I'll be more than happy to work through some additional examples with you. So let's jump in and review the rules for significant figures. The first rule we have is that when you're recording a measurement, when you're writing down the number that goes with the measurement, any non-zero digits are always significant. And so if I look at these three different numbers, if these represent some kind of measurement, how many significant digits are there? Well, here, obviously there's three because there's 1, 2, 3. These are all non-zero. And so every one of these is going to be significant. This one has 5 significant digits. This has 4 significant figures. And so I think you'll find this pretty straightforward. The second rule has to do with zeros. So we looked at non-zero in the last slide. In this slide, we're saying all zeros between significant digits, between non-zero numbers, are also always significant. And so if I've got 504, the 0 is in between the non-zero number, so those are significant. So this has 3, this has 1, 2, 3, 4, 5 significant digits. This one obviously has 4. These zeros in the middle, they are significant. When trying to determine which digits are significant or not, it's the zeros that can be a little bit tricky. Now, we've already seen that if the zeros are between non-zero numbers, they're significant. What about other zeros? Well, if the 0 is a final 0 to the right of a decimal point, then those zeros are significant. So I've got 32.0. This would have 3 significant figures because this 0 is significant. Why? It's to the right of a decimal point. Here, I've got 3 zeros to the right of a decimal place. This one is the final, and so this 0 is significant. These non-zeros are significant. These are all significant because they're in between 2 significant digits, and so that tells you that this whole thing has 5 significant digits, or 5 significant figures. Now, here, I've got this long number, and I've got this final 0 here. And notice I've got it final there in red here. This final 0 is also significant because it's to the right of a decimal point. And so I can count up 1, 2, 3, 4, 5, 6, 7, and I have 7 significant figures from this measurement. The next rule, and this is maybe the trickiest one, all zeros that act as placeholders are not significant. This is really the time when the when the zeros are definitely not significant. And what do I mean by placeholder? Here in this digit that I just wrote down, I have some zeros and they're to the right of the decimal place, but they're not final. If there was a 0 over here, that would tell you something. But these guys are basically just placeholders. They're telling you that I don't have 34 or 3.4. I've got 3.4 divided by 1,000. These are telling me that this number is smaller than 1, and each of these zeros represents division by 10. So as you go from place to place. And so these don't have anything to do with the actual measurement. They're just placeholders for the actual measurement, which would be 3.4 or 34, whatever it is. Now, if that was confusing at all, there's another way to say this, and it's just zeros are only significant if they are between significant digits or if they happen to be the very final thing at the end of a decimal point. Those are the only times when the zeros are definitely going to be significant. So let's look at some quick examples. What about this one? How many significant figures does this guy have? Well, these zeros are all placeholders, and then you have a 2, that's 1 significant digit. Here, I've written a number out in scientific notation. This is 6.02 times 10 to the 23rd. That would be moving this decimal place over to the right 23 times. But how many significant figures? The 10 to the whatever doesn't count. So how many significant figures does this have? You would say it's 3, because you've got the 6 and the 2 are non-zero. The 0 is in between them. It's therefore significant. I have 3 significant digits or 3 significant figures. What about here? I've got a 1, which is significant because it's non-zero. I've got a 0 to the right of a decimal place at the end, so that's significant. All the numbers in between are significant, so I've got 1, 2, 3, 4, 5, 6, 6 significant digits. Now what about this guy? There's no decimal here. I can't tell whether any of these are significant or not. And so we would say that that's ambiguous. We're going to learn how to deal with these ambiguous situations in a minute and make the other rules apply. But I just want to point out, you've got these zeros are not after a decimal point. And so if there was a point 0, a decimal point and then a 0, then all of these guys would be significant. But without that, you can't say that these guys are significant or not. You just don't know. Same thing with this guy, 800. I can't say definitively how many significant figures this guy has because these zeros are ambiguous. Now, what does that mean when I say that these guys are ambiguous? What I mean is that this could be 800 plus or minus 1. That means the measurements between 799 and 801. Or it could mean that it's 800 plus or minus 10, in which case it would be between 790 and 810. There's a big difference between those two uncertainties, and I don't know which it is just writing the numbers out like that. Now, the way that I can fix that is to write these ambiguous numbers out in what we call scientific notation. And that's like what we have up here. This is a number that's written in scientific notation. And you can see that I've got 6 point blah, blah, blah. So in scientific notation, you've got your number, you express it between 1 and 10, and then you have some power of 10 up here. And so I could express this 800 as 8.0 times 10 squared. And that would tell me that this guy has 2 significant figures. Or I could express this as 8.00 times 10 squared, or 10 to the second power. And that would tell me that this guy has 3 significant figures. And so this would mean that this is 800 plus or minus 1, and this would mean this is 800 plus or minus 10. And so that's basically building in that uncertainty. So with scientific notation, again, we can use scientific notation to help us figure out how many significant figures there are in a number. If you're ever confused about how many significant figures there are, if you're not sure, put the number in scientific notation. That will make it super easy to determine how many significant figures there are. And scientists also love scientific notation because we deal with a lot of times very, very large numbers or very, very small numbers, which are very cumbersome to write out all the digits. And so we can express them using scientific notation in significant figures in a very compact way that makes life easier for us. So again, with scientific notation, you have a number that's between 1 and 10, and then it's multiplied by some power of 10. 10 to the 2, 10 to the minus 3, whatever that is. And the exponent of the 10 can be determined by the number of decimal places you have to move to get only one number in front of the decimal. If the number you start out with, let's say we're talking about large numbers, if the number you start out with is greater than 1, the exponent will be positive. So let's look at the number 39,923. How would we write that in scientific notation? Well, the first thing we want to do is move the decimal until only the first number is in front. And so I've got the decimal place would be right here. I'm going to move it 1 time, 2 times, 3 times, 4 times. And so now I've got it written out as 3.9923. Now, I want to determine the exponent, what number goes with the 10. I simply count the number of decimal places that I moved. So I moved 1, 2, 3, 4 times. And so now I can write this out as 3.9923 times 10 to the 4th because I've moved it 4 places to the left. Now we can look at also small numbers, that is numbers that are less than 1. So if the number you start out with is less than 1, say let's take this one, this is 0.0052, obviously that's less than 1. We want to put that in scientific notation. We're going to move the decimal place over until we get it so that there's only one number to the left of the decimal. And so we'll move that number over until we end up with 5.2. So that means 1, 2, 3 times. Now we want to determine the exponent. 5.2 times 10 to the what will give you 0.0052. Well, obviously we have counted over 3, and so we're going to move to the exponent is going to be to the minus 3. So in other words, we've moved this decimal place 1, 2, 3 decimal places to the right. And so 5.2 is bigger than 0.0052. So I need to basically divide by 1,000 to get it back, or multiply it by 10 to the minus 3. And that 3, we just count how many times we move the decimal place. 1, 2, 3, there we go. So here are some examples for you. I have some numbers with the goal of putting them in scientific notation. And on the next slide, I've got all the answers. But I'm not going to do all of these, but let's just look at a couple. How about this one? If I want to put this in scientific notation, I'm going to need to move the decimal place over to the left one time. And so that would be, I move the decimal place over one spot, and so that's going to put it as 9.9343, and then I need to go from 9.9 to 99, I'd have to multiply that by 10. And if I'm being really careful, that's really 10 to the 1 power. And by the way, if my number, instead of being 99.3, what if it was already just 9.934? How would I put that in scientific notation? Well, I could write that as times 10 to the 0 power, because anything to the 0 power is just 1, right? Hopefully you guys remember that. And so that's one way to look at that. Now, let's do one more of these, and I'll let you work on the others on your own. This guy here, obviously this number is smaller than 1, so we're going to move the decimal place to the right 1, 2, 3, 4 times. So that would be 3.75 times 10 to the minus 4. And it's that easy. And as I said, I expect you guys have done this before in chemistry. If you haven't done this before, it's not that hard. Work through the rest of these examples and then check your answers on the next slide. And so you can see here are the examples on the next slide. You can see the two that we did just then. The others you can do on your own. And of course, it's worth mentioning that you might have a number that's already written in scientific notation, and you might want to go to its decimal equivalent, that is, just write it as a regular number. And we just reverse that process. You just multiply it by, you just move the decimal place over by however many times the 10 to the exponent tells you to do. And of course, if your exponent is positive, you expect the number will be greater than 1, and if the exponent is negative, the number will end up being less than 1. It'll be a decimal. So here are some more examples you can practice with. Let's just do a couple of these. I'll let you guys work on the rest. How would I put this guy, 3 times 10 to the 6 in scientific it's in scientific notation. You could say this is 3 point or just 3. 3 times 10 to the 6, well, that's just going to be, we're going to take that decimal place and move it over 6 places. In each place we move it over, we're going to get a 0, so that would be 3 million. So that 3 point has moved over 1, 2, 3, 4, 5, 6 places, and so that would be equivalent to 3 times 10 to the 6. Let's look at this. 8.45 times 10 to the minus 7. And so I'm going to move that decimal place to the left 7 times. And so that means I'm going to move 1 time here, and then I'll do it 6 more times. So that means I'm going to have 6 zeros in front. And so this is going to be 0 point. I need 1, 2, 3, 4, 5, 6. 845. And if I go in the opposite direction, I'm going to have that be 1, 2, 3, 4, 5, 6, 7. And so this would be 8.45 times 10 to the minus 7. And so you guys can follow that pattern, do the rest of these on your own, and see how that works out. And of course, here are the answers that you can use to check yourself with. Now, the next slides is dealing with the significant figure rules for mathematical operations. That's a mouthful. The basic idea is this. When you make a measurement, the significant figures are what we can use to estimate the uncertainties associated with that measurement. Any measurement, the time that something lasts, you could measure with a stopwatch. The length of something, you could measure with a ruler. Any of those measurements is going to have that plus or minus part, that uncertainty that goes with it. And significant figures are one of our ways that we can keep track of those uncertainties. Now, let's say I have two links and I want to add them together. I've got two different measurements of two different lengths and I want to add them together to get the total length. What's the uncertainty of my total length? How do I combine those uncertainties? How do I keep track of the uncertainties of my answer? Or, for example, if I have, let's say I have a tabletop and I measure the length and I measure the width of the tabletop and I multiply those together to get the area, well, each of these lengths, the length and the width, they're going to have a plus or minus part. They're going to have an uncertainty. How do I keep track of the uncertainty of my area? And the answer is I use my significant figure rules. They will help keep track of the uncertainty of the product of the two numbers that I'm multiplying together, or the quotient of them if I'm dividing them. Let me say all of that fancy stuff in a simple way. When I apply the significant figure rules for mathematical operations, I'm keeping track of my uncertainties of the result of those mathematical operations, whether it be addition or multiplication or something else. Now, the vast majority of operations that you're going to do are either addition, subtraction, or multiplication, division. And remember, addition and subtraction are really the same thing. Subtraction is just addition of a negative number. Division is just another kind of multiplication. In other words, I could divide by 2 or I could multiply by a half. It's the same thing. So let's look at how we handle significant figures when we are adding or subtracting the results of two measurements together. And so the rule is when adding or subtracting two or more numbers together using significant figures, the answer should have the same number of decimal places as the number with the fewest number of decimal places. That's not the same number of significant figures, it's the same number of decimal places. So addition and subtraction, you keep track of decimal places. That's very important. So let's look at a couple of examples here. I've got two measurements here, 11.4 centimeters plus 2.32 centimeters. It doesn't matter how many significant figures these guys have because they are being added or subtracted. And so I keep track of the number of decimal places. This has 1 decimal place. This has 2 decimal places. When I add them together, my answer should keep the least number of decimal places. In this case, it would be 1 decimal place. And so I add these together, I get my total is 13.72, but according to the significant figure rules, I only keep the 1 decimal place. And so I end up, this sum should be 13.7 centimeters. So I've got 11.4 centimeters plus 2.32 centimeters. I end up using the significant figure rules for addition, 13.7 centimeters. Now let's look at another example. Subtracting two distances. I've got 15.2 centimeters minus 4.82 centimeters. This guy has 1 decimal place. This guy has 2 decimal places. So how many decimal places should my answer have? Well, I look at all the numbers that I'm adding or subtracting, and I count how many which one has the fewest number of decimal places, and that would be this guy, which has only one decimal place. So my answer, when I add them together, I get 10.38, but I should have only one decimal place. Now, because this is 338, I'm going to round up and make that 10.4. So 15.2 centimeters minus 4.82 centimeters should give us 10.4 centimeters. That's using the significant figure rules for addition and subtraction. Now, I have note bien, which is French for note well. When adding or subtracting, you use decimal places, not significant figures, to determine how many digits your answer contains. So let's look at one last example. I've got 1.003 meters plus 0.21 meters. This guy has 4 significant figures. This guy has 2 significant figures. None of that matters. The sig figs don't matter when you're doing addition subtraction. What matters is the number of decimal places. And so when I add these guys together, I get 1.213, but the rule tells me to keep only the same number of decimal places as the one that has the least. In this case, this guy has 3 decimal places. This guy has 2 decimal places, so my answer should only keep 2 decimal places. And so I take this 1.213 and I lop off that 3, that gives me 2 decimal places, and my answer, 1.003 meters plus 0.21 meters, gives me 1.21 meters. Now we can look at the rules for multiplication and division. When multiplying or dividing 2 or more numbers together, the product or quotient should have the same number of significant figures as the factor with the fewest number of significant figures. So with addition and subtraction, you track decimal places, but with multiplication and division, you track significant figures. And you multiply a bunch of things together or you divide them, you find the one term that has the fewest number of significant figures, and that tells you how many significant figures your answer should have. So let's consider this example. I've got 1.2 centimeters divided by 0.0346 seconds. We're doing division, so we count significant figures, not decimal places. So this guy has 2 significant figures. This guy has 3 significant figures. How many significant figures should our answer have? Hopefully you shouted out 2. We should have 2 significant figures. So if I do this division and plug it into my calculator, I get 34.682 centimeters per second. Now, how many significant figures should my answer have? It should have 2. This one has 3, this one has 2. I use the term that has the fewest number of significant figures, which in this case is 2. So my answer should have 2 significant figures. Now I'm looking at this 34.6. I know I'm going to want to round that up to 35. And so 1.2 centimeters divided by 0.0346 seconds gives us 35 centimeters per second when we apply the significant figure rules. I will say it can be hard for students sometimes. Man, some of my students, they really want to put that decimal point in there. They want to say 34.6 or 34.7, but really it should just be 35 because that's what the rules tell us. Now let's look at another one, and you might recognize this formula. I've got 3.14 times 0.35 squared. This is, of course, pi r squared. This might be the area of a circle. And so what does it mean to square something? Well, it just means multiply it out. And so we're going to use multiplication rules. So I've got 3.14 times 0.35 meters times 0.35 meters. And when I do that, I get 0.38465 meters squared. Now, how many significant figures should I have? Now, this 3.14, that's actually 3.141592654, and a whole bunch of other numbers. In fact, there are infinitely many numbers in pi, digits in pi, and so pi has infinite significant figures. It's not going to ever affect, your final calculation. So these guys have 2 significant figures each, so my answer should have 2 significant figures here. So I'm looking here, 0.384. That 4 is less than 5, so I don't round up, and I'm left with 0.38 meters squared. And that's my answer. Now, most of you may have seen how to do significant figures of addition and subtraction or multiplication and division before, and that's great. You may or may not have seen how to apply these rules to different kinds of mathematical functions. So, for example, the trigonometric functions like sine and cosine. And so, let's say I measure an angle to be 43.5 degrees. And so I've got 43.5 degrees, and I want to know the sine of that angle. How many significant figures should I have? Well, you may think it should be 3, but let's check and see what goes on. So if I plug in the sine of 43.5 degrees, I get 0.68835. And if I increase the 5 to 6, that's just a little change. So I've got the sine of 43.6. I got 0.689619. And so let's look at my answer here. Both of these guys have 0.68. So in this change, this 0.68 hasn't changed, but the 8 has changed to a 9. And if I do the sine of 43.4, I get 0.687, it turns out, some other stuff. So these two digits here, they're certain. Because of this small change, I'm still going to have 0.688. If I misjudged my angle a little bit to the small side or a little bit to the big side, this is going to be the digit that's uncertain. And so that would tell us that we get 3 significant figures. And so if I take the sine of 43.5, I'm going to say that I should keep 3 significant figures. And so that would be 0.689, rounding this guy up. And so that would be what I would expect for the sine of 43.5 if I was applying the significant figures approach. Now, you might think, okay, I've got 3 significant figures of my angle, I got 3 significant figures of my answer. So is that the rule? Actually, it's not. Let's look at a different angle. Let's look at 88.8. And so if I look at 88.8, I get 0.9997. And if I look at 88.9, I get 0.9998. And so these 3 are the same, and I have to go to the 4th decimal place to get any uncertainty or any variation. And so these guys would be certain, and this guy would be uncertain. And so this guy would actually have 4 significant figures. What? What's going on? How can it have 3 significant figures for one angle and 4 significant figures for the other angle? The answer has to do with the way that the sine function works. So if I'm at about 45 degrees here-ish, you can see that my sine function is increasing very rapidly. So if I change my angle a little bit here, I get a pretty big change in my sine function. But if I'm close to 90 degrees, where the sine function is a maximum, the sine function is kind of flattening out. And so from here to here, there's not as much of a vertical change. That is, my sine isn't changing as much as I change the angle. And so the uncertainty actually here of this function is actually less than it would be over there. And so that's why you can have different number of significant figures for sine and cosine. Now, do you really have to worry about that? No, I'm not going to care if you put 3 significant figures when you should have really had 4 significant figures. But I wanted to point it out because I do think it's interesting, and it does show you that, this stuff is probably a little bit deeper than you realize. And so it's maybe kind of an interesting point to make about that. Now, the last thing I want to go over is how to round numbers up. I think you all learn how to do this, but you may be surprised that I find that my students, there's one piece of this that they don't know. Very often they're missing one little thing. But let's just go through it real quick, and then we'll end this video. So if I want to round, I've got some significant figures. I multiply them, I add them, subtract them, whatever. I've got my answer, and I need to determine the correct number of significant figures in my answer, and I'm going to know, do I need to round up or not? I've shown you some examples where I've done some rounding. The rule's pretty simple. And so let's consider that I've got a bunch of numbers here and I want to round them all to 1 decimal place. So the rule is that if the number to the right of the number you want to round up is greater than 5, you round up 1 digit. Otherwise, you don't round up. And so 4.68, I want to round to the 6, I want to round to the 1 decimal place. 8 is bigger than 5, so I need to round that 6 up to 7. That gives me 4.7. Now I have 4.62. The 2 is less than 5, and so I want to not round this 6 up because this guy's less than 5, and that gives me 4.6. Now, what about this guy, 8.2503? Well, this 503 is bigger than 5. You would really say it's bigger than 500, but it's bigger than 5, so we're going to round that 2 up to 3. It's that simple. Now, what you probably are like, yeah, I know this, Dr. McPherson. I know all this stuff. What are jibber jabbering about? Well, here's the part that you might not know. What if it's exactly 5? The number to the right of what you want to round up is exactly 5. Then you only round up if that number is odd. In other words, let's look at this number here. I've got 6.8500, not 501. If it were 501, you'd round this 8 up to 9. But it's 500. It's exactly 5. And so the rule says I don't round it up if this guy's even. I only round it up if it's odd. And so I don't round, it's 6.8. But if I've got 4.35, and this is exactly 5, there's no non-zero numbers beyond the 5, this 3 tells me that that guy's odd. So if this number is odd, you round it up. If, however, it's even, you don't round it up. And I bet you never learned that before. And if you did, I'm impressed because a lot of my students haven't seen it before. Why is that the case? Because basically, you're saying half the time you round up and half the time you don't round up. And so if you always round it up every time that you got exactly 5, that would create just a little teeny tiny bias towards rounding up. And this is just a way to kind of balance out that bias a little bit when dealing with lots and lots of numbers. And so that's it. That's significant figures in a nutshell. I will see you guys in the next videos.